presentations on detecting aberrations in EUV lithography systems. So let's just start by breaking this down. EUV lithography is a method of photolithography, which is essentially using light to cut grooves into metals. In this case, we're using it to cut grooves into silicon in order to create microprocessors. So EUV stands for extreme ultraviolet, and we're looking at wavelengths of around 13.5 nanometers for various reasons. The reason that we want to use extreme ultraviolet rather than the current industry standard of deep ultraviolet is because feature size is directly correlated to the wavelength of light. So theoretically, if you could use the exact same system, then 13.5 nanometer light would create features of more than 10 times smaller than that of deep UV, which is 193 nanometers. Because of these reasons, most corporations regard EUV as the next step for creating microprocessors. But the problem with creating such small features in EUV is even the smallest aberrations in focus can drastically alter your results. And because lenses are imperfect, this is quite common, and this will greatly decrease the resolution. In order to further clarify the concept of aberration, how many of you here have astigmatism or are nearsighted or farsighted? Yeah, see, those are all aberrations. And yeah, we do not want those in EUV. So, to further explain, in an ideal lens, if you pick a single point, no matter what angle you light shines at from that point, it will always focus to the same place. And you can see this in our diagram right here. See, whether you go to the top, middle, or bottom of the lens, you will always focus to the same place. However, in an aberrated lens, this is not necessarily the case, because in this aberrated lens, the top focuses much farther than the bottom. And the explicit reason why we do not want aberrations is because this greatly increases our feature size. In an ideal case, we'd only be limited by the diffraction of light, which gives us a minimum feature size that's directly correlated to the wavelength. However, in an aberration-limited system, we do not necessarily focus to the same point, which increases our feature size. So therefore, our goals for this project were to create an efficient method of detecting aberrations that works in the context of an EUV system. Because EUV systems must be contained in a vacuum, this system must also work inside a vacuum, and due to that, cannot use a multi-pixel detection system, and we're pretty much limited to a diode, which is essentially a device that checks how much light it is absorbing at any given point in time. So the solution is to use two gratings. The first grating will be imaged through an optic onto a second grating. And the second grating will be able to move side to side and up and down on a stage. And as we move that grating, the signal on the diode is going to change. If the first grating that we are imaging is in focus, and if images right on top of the second grating, then no light is going to get through because all the light from the grating will be blocked by the second grating, which creates a signal of 0 on the diode. As you move to a completely out of phase section, then all the light will make it through because the grating will block none of it, creating a very high signal on the diode. And this creates a very high contrast signal. However, when the grating is out of focus, it will be wider and more blurrier than it is normally, which makes it so that not all the light is blocked when you're in phase, and not all the light makes it through when they're out of phase, which creates a very low contrast signal. So by moving around the grating, we can find this part with the highest contrast, which is then the focus of that section of the lens. And in order to scan multiple sections of the lens, we will be using the miracle, and that is essentially a mirror controlled by 4 piezoelectric rods, which is a complicated way of saying that you can use electricity to make the mirror move around very freely, very quickly, and in a very wide range of motion. As you can see, it's pretty good because I can write my name with it, and I'm kind of vain like that. The problem with the miracle is that there's a resonance frequency, and if you approach this resonance frequency, it can break and wash a few grand down the drain because you don't like breaking things. And this is essentially what we're using the miracle for. This is a very scaled up version of a scanning algorithm that we wrote that essentially, given a radius and the location of the center of the circle, it will scan in a spiral in and out And we will be using this to scan onto a section of the lens. There's various issues with our proposed solution, however, and essentially, this is it. I do not know where I put my grading, so I'll just get something next. So when we shine light through this grating, you see this is the ideal situation. We have 3 dots, 1 in the center and then 2 on the outside. This is a sinusoidal grating, which creates a bright 0 order and 2 first orders, but nothing else. However, in an alternate solution, which I seem to have dropped somewhere, it's a square grating.
Use your imagination.
What happens is there will be 1 dot right here, and then there's pretty much going to be an expanding square of grading, of small dots. And this really messes up our solution because it will create false maximums and false minimums, which will essentially prohibit easy detection of high contrast. However, this is the good one was a sinusoidal grating, which means that it's a continuous function, but because of manufacturing constraints, we're stuck with binary gratings, like the square grating, that would make many harmonics. So the solution to simulate a sinusoidal grating is to combine 2 different gratings. The first is a 50% duty cycle square grating. Duty cycle, as Vincent explained, is the relationship between the width of the grating and the entire distances between 2 parts of the grating. The 50% duty cycle square grating will suppress even orders, which means that every other dot will be taken away. A 40.4% duty cycle hexagonal pinhole grating, on the other hand, suppresses every 3rd order, which means every 3rd dot will be taken away. So if you think about it, we'll be left with 0 order, 1st order, and then 5th order, and then etc. from there. But 5th order is already so small that we can essentially neglect it, and it essentially models a sinusoidal grating. Another advantage of the 40.4% duty cycle hexagonal pinhole grating is that it provides 6-way symmetry, which allows us to create a more detailed and better map of the aberrations. However, the problem with our 40.4% duty cycle hexagonal pinhole grating is that it's very memory intensive to generate because each pinhole is regarded in the CAD program as a 256-sided polygon, and it's inefficient to generate. So when you consider the vast scale of these gratings, we ended up using 800 megabytes for about 9 gratings. And this is a very scaled down version of our hexagonal pinhole grating. And the solution to compress this file in order to make it easier to send to manufacturers was we only drew the circle once. Every other point was we passed the location of these orange dots, and then to those locations we also passed a distance and a number, which told it to redraw the same circle, which we only drew once and is only stored once in the memory, at that point, and then again every certain number for a certain number of times. These are some more images of our 50% duty cycle square grating, and it's quite literally just a lot of really thin, long rectangles stacked on top of each other that are spaced evenly. And you can see that we have in 3 different orientations. The first one goes like this, another one goes like that, and this one's just vertical. As I said before, this matches up with our 6-way symmetry of the hexagonal pinhole grating and allows us for better resolution. So in order to make this all work, we needed an optical setup that fulfills a few requirements. First of all, we need at least a 0.1 numerical aperture. Numerical aperture is most easily regarded as the range of angles that light can pass through a lens. Furthermore, the light must hit the grating at the same spot no matter what angle we're scanning at. And the light must also be focused onto the test optic. Finally, we need this all to be contained in a compact system, so hopefully it fit within about half a meter to maybe a meter. Something odd just happened. Okay, so we came up with a solution that involves 3 lenses. Light from the laser comes out and then hits the first focusing lens, which then passes through and bounces off in the miracle into a direction somewhere off over there. But in order to make this 2-dimensional, we kind of just folded it out. The light will then focus and then pass through a condenser lens, through the square grating, onto the test optic, then onto the pinhole grating, and finally onto the diode. So there are a few main features of this optical system that make it ideal. First of all, The miracle and the square grating are conjugates. This means that the miracle images through the condenser lens onto the square grating. This results in a constant spot on the square grating no matter what angle the miracle is pointing at, because the laser spot on the miracle is always the same. It's merely changing angles. Another set of conjugates that we create is the focus light from the focusing lens and the test optic itself. This creates a small dot on the test optic and allows us to have better resolution. So we substituted our two gratings in as a square grating and a pinhole grating. So although we may not have the complete cover and the complete disc, like not in phase, the principle of finding the spot with the highest contrast will still apply. So as a result, we built this system in the optics lab, and it looks pretty cool in the dark. And unfortunately, we have not yet ordered the masks. So yeah, we cannot actually have any results because there's nothing to actually test yet. So looking to the future, we want to confirm the size and the size of the gratings in the mask, order the mask, get it shipped over here, and then add the masks and the stage to the optic system to test a lens with known aberrations. This would allow us to know whether or not this method that we proposed is actually verifiable and efficient. And yeah, I'd like to say thanks to my mentors, Ryan and Rick, as well as everyone from LBNL who worked with me, and all the people from the SHARP program like Avi, Evie, Dr. Chong Hasning, and Aaron. So yeah, thank you. Any questions? Yeah?
Did you find the other grading, the bad one?
Yeah. I can look for it while you guys ask a question or something.
The sample that you have, you use the green laser to shine through. See what happens.
Okay.
Should work.
Where's the green laser?
You should shine both at the same time.
Good idea.
That way you
It's
can
just a
see.
little brighter.
You
And
can
as
see.
you can see, like, yeah.
You'll see the separation between the red and the green.
Yeah, and then there's extra stuff, but that's just because it's kind of like bouncing off the lens and my shirt and stuff. So those aren't actually supposed to be there. Yeah?
Can you say more about your choice of the 40.4% pinhole grading? How did you come to that choice?
Honestly, I don't really understand the math behind it, but essentially what happens is when you use the Fourier transform to look at it in the frequency domain, 40.4% duty cycle apparently exactly suppresses the third order when you make the cover. I'm sorry, I can't explain in more detail. I just know the general part. Any other questions?